So let's take a look at an example of the projection theorem in action. So in this example, we've got two vectors in R3. We've got u and a given in terms of their coordinates right here. So we're asked to find a decomposition u is equal to w1 plus w2. So in other words, to break u up into the sum of two vectors w1 and w2 such that w1 satisfies the property that it's parallel to the vector a, and w2 satisfies the condition that it's orthogonal to a. That's what these two statements here are saying. So, okay, great. We can do that. Why do we know for sure that's possible? Well, simply because a is non-zero. That's why it's guaranteed by the projection theorem, right? Because as long u and a can be any vectors in Rn as long as a is not equal to 0, then there's guaranteed to be a unique decomposition. You can break u up into w1 plus w2. There's guaranteed to exist some choice of vectors w1 and w2 such that both of these conditions are satisfied. And that's exactly what's asked for in this example. So we'll use the projection theorem to do it. So the first step is going to be to find w1, and we'll just use that, we'll do that using the projection formula. So that's the first step, just to find w1. And we're just going to take the projection of the vector u onto the vector a. So that's what we're going to calculate. And the formula for that is just take the dot product of u with a and divide it by the dot product of a with itself. That's part of the formula, right? We want to take that, form the scalar that you get if you calculate the numerator and denominator of that fraction, and then take the scalar product of that scalar with the vector a. So now work out the numerator and denominator of this fraction. So u dot a, first of all, right? That's the numerator. Well, we want the dot product of u with a. So just work it out. We're going to go 2 times 4 plus -1 times -1 plus 3 times 2, and that's the dot product. So let's work it out. We've got 8, +1, and 6, right? So 8 plus 1 is 9, plus 6 is 15. Okay, now we're going to work out the dot product of a with itself. That's the denominator of this fraction. So the dot product of a with itself, well, it's just going to be 4 times 4, because the first coordinate of both of these vectors is 4, right? Because they're both the same vector a. The second coordinate of both of those vectors is -1. So we'll have -1 times -1. And then the third coordinate of both of those vectors is 2. So we'll have 2 times 2. So we've got 4 times 4, which is 16. This will be +1 again, so that'll make 16 plus 1 is 17. 2 times 2 is 4, so you get 17 plus 4, which is 21. Okay, well that means this is really just 15 over 21 times the vector a. Right, and if I could put brackets there if I want. So that's what this projection ends up being. But 15 over 21, you can reduce that actually. They've got a common factor of 3 in the numerator and denominator. So we can actually write this as 5 over 7. And then, well, let's actually use the vector a, 4, -1, and 2. So that is our vector w1. Now, if you want, you can multiply the fraction into the vector, and you'll get 20 over 7, because 4 times 5 is 20 for the first coordinate, and then you'll get -5 over 7 for the second coordinate, and then you'll get 10 over 7 for the third coordinate. And you can see right away, this is a perfect example of why sometimes it's nicer just to write it like this, right? Then you only have to write one fraction rather than writing 3 fractions, 1 fraction for every single coordinate. However, it's going to turn out in this case that it's nice to have access to w1 written out coordinate by coordinate, because, well, this is w1. How do we get w2? Remember, we have to just take w1 and subtract it from u. So just take w1, subtract it over to the other side of the equation, and that's how we'll get w2. And it's going to turn out that in order to do that, it's going to be convenient to have w1 written out in this fashion. So we can now go w2 is equal to u minus w1, right? So u is equal to, well, 213 or pardon me, 2, negative 1, 3, minus this vector here, 20 over 7, negative 5 over 7, and 10 over 7. And it's probably useful to write all three of these coordinates so that they have a denominator of 7 that matches up with these coordinates, and then we can perform the subtraction a bit easier. So let's write this as, we'll write 2 as 14 over 7, because that's really what it is. Negative 1, we can write that as negative 7 over 7. And then 3 we can just write as 21 over 7. And then we'll subtract W1 here, which is 20 over 7, negative 5 over 7, and 10 over 7. So just subtract coordinates, one coordinate at a time. 14 over 7 minus 20 over 7 is going to give you negative 6 over 7. Negative 7 over 7 minus negative 5 over 7, that's like plus 5 over 7. So negative 7 over 7 plus 5 over 7 is going to give you negative 2 over 7. So that's your second coordinate. And then our third coordinate, 21 over 7 minus 10 over 7, that's going to give you 11 over 7. So that will be our W2. So let's summarize, right? This is all our work. Let's summarize up here. We got room, so we can say therefore W1. We got two different ways to express W1. You can use this expression or you can use this expression. Since the other one has fractions, let's just write them both using the fraction form. But it's totally, you have the freedom to choose how you want to express your answer as long as it's clear. I would go with one of those two forms, but let's go with the second one. So 20 over 7, negative 5 over 7, and 10 over 7. And then W2 will be negative 6 over 7, negative 2 over 7, and 11 over 7. And then we can just put a box around that and identify that this is our decomposition. These are the two vectors, W1 and W2, that were really asked for in the question. We wanted to find this decomposition. Really, that means find these two vectors, and that's exactly what we did down here. So that's an example of using the projection formula. Now, why would you ever want to do this? Who cares? Or like, why is this ever useful? I want to answer that question with an application. So this is probably the best application of projections in the sense that it's simple. It doesn't involve a lot of machinery. It just involves some basic terminology and objects that we've already been talking about in this section. And but it's also concrete enough. It actually gives you something that you wouldn't be able to get otherwise. So in the sense that you wouldn't be able to solve this problem without projections. Although, and I would argue if someone contradicted me and said, well, I can actually solve it without projections, and if I took a close look at their work, I'm willing to bet that what they would be doing is probably exactly what projections are doing. They just wouldn't be calling them projections. So you genuinely do need projections to solve this problem. So let's go through it. Given a line, L, and some point, P, which happens to not be on the line. So you got your line and then some point, which is some distance away from the line. And the question is, well, what is that distance? Okay, so the picture here is you've got a line, which I'll call L. And to be honest, it's not going to be really important that we call it L, but just it's a tradition to give things names, I guess. And then we've got some point P that's not on the line, right? And the question is, how far away is this point from the line, right? And assume that you've got all the things you might expect that you'd need, right? Let's say, assume you're given the coordinates of this point, right? I didn't write any down because I'm trying to draw a general idea here, but assume that this point has let's assume we're in R2, just to keep things simple, and assume you've got an x coordinate and a y coordinate of this point P. And let's say you've got the equation of this line in the form y equals mx plus b, or maybe you want point normal form or point slope form, slope intercept form. Let's say you had absolutely any information about that line that you wanted. And the question is, how far apart are they? So what does that mean to say how far away is the point P from the line L? Well, what's the distance between a point and a line? Well, we know what it means to take the distance between 2 points, but between a point and a line, well, I mean, you could just pick a point on the line, right? I could just pick a point right there and then just draw a line segment between the point and that line, and I could measure that line segment. But I bet you that you're watching this video and you've already started shaking your head thinking that that can't be the right way to go. Who would ever do that? Pick this point of all points? I mean, why not pick this point over here then? If you're gonna just pick a random point, that isn't what you really want, right? That can't be what we mean when we say the distance from the point P to the line L. If anything, what we really mean is there's some point on this line that's the closest to the point P, right? There's some point, who knows what it is. I'm going to draw a question mark there because we don't really know what it is. But if that's the right point and we want to measure this distance using that point, then it had better give us like a right angle here. That would make sense, right? If we could get our hands on that point though, but who knows? We don't know what that point is, right? That's the real problem. If you knew what this point was, well then great, you could just take the distance between those 2 points using the distance formula and you'd be laughing. You would have solved the problem. But the problem is we don't know what that point is, right? So that's the problem. So I'm going to erase this because I want to now redraw some things that are a little bit more permanent here. But that's the idea. Okay, so how are we going to find the distance between this line and the point P? Well, the first thing we're going to do is we're going to just pick any point Q on the line. So here's our steps. I'm going to write these down. So pick any point Q on the line. Right, so the only restriction that you're putting on Q here is that it has to be a point on the line. It can't be a point off the line or this won't work. But you don't have to pick any point in particular. You don't have to pick it to be that closest point because, well, how would you? You don't know which point that is. So you could pick this point, this point, this point, this point, anything on the line is fine. I'm going to draw this one because then that makes the picture turn out the way I want, but there's no reason that it has to be this point, right? It could be any point on this line at all, but I'm going to pick that point and I'm going to call it Q. Okay, and the next step is easy. All you want to do is form the vector U and just take the geometric vector that starts at the point Q and ends at the point P. Okay, so we're just going to take this vector right here. That is your vector U. Okay, and now the third thing we're going to do is we are going to find the direction vector of this line L. Really what I mean by that is we need to find some vector that points in the direction of L exactly. And I'm guilty of using this language maybe over and over and over again on the previous pages, but this is the best way that I can think of to say it. We need to find a vector that has the following property. When you draw it so that its initial point lies on this line, then its terminal point also lies on this line. That's what it means to be the direction vector of this line L. So we need to find, and there's more than one option of vectors that satisfies that condition, but we don't need to find them all, we just need to find one of them. So find the direction vector of L. And let's give it a name. So call it A. So in general, you can take any vector who satisfies the property that if its initial point is drawn on L, then its terminal point is also. But I'm going to draw it specifically over here so that so the picture turns out the way I want. So we're going to draw our vector A as if it's exactly like that. So I'm going to draw A like that. Okay, and you might start to recognize this picture. This picture's starting to look a little bit like our projection picture on the previous page, and that's if you've noticed that, then great. But it's no coincidence that this is starting to look like the projection diagram for the projection theorem. But before I go on to step 4, some of you might still be thinking about this that I just wrote down. Find the direction vector of L and call it A. Well, how do you do that? Right? Well, one way would be just to pick 2 points on the line. Right? If you have the equation of the line, it shouldn't be too hard to generate 2 points on the line. Right? Just pick 2 x values, plug them in, get their respective y coordinates, and then now you've got 2 points on the line. Now you just form the geometric vector from one of the points to the other, and now you've got the direction vector of the line, or at least some representation of it. But it turns out there's another way that's quite easy, and I'm just going to mention it. It's a little bit of a shortcut. Remember, if you have the equation of the line, let's say, let's add it in. Let's say it's written in slope-intercept form, so it's y equals mx plus b. So I'm just adding that in. Let's say that the line is given by this equation. Well, then you can use that slope to get the direction vector really quickly. Just take the vector a to be 1m. Whatever the slope of the line is, take that to be the y, the second coordinate of the vector, and take the first coordinate to be 1. That will always work. Okay, so that's kind of like a little mini formula within this process. Okay, you don't have, that's only one way to do it, but again, there's many different ways to get the direction vector of the line, but sometimes people just would like to have one way that's guaranteed to work, so use this way if you're one of those people. Okay, so now we're actually almost done, because what we're going to do now is we're going to set, and this again, the notation is going to look familiar, we're going to set W1 to be the projection of the vector u, which we've drawn up here, onto the vector a. So we're going to project u onto the direction vector a, and we're going to get, what we're going to get from that is this vector here. It's the component of u that is parallel to the vector a. That's really what the projection of u onto a really gives you. So that's going to give you this vector. This is your W1, and we know that from the projection theorem. That's really what the projection gives you. You can always, where is it? If I go back to the page where we did the projection theorem, if you have a vector u, and you've got some line that goes through the initial point of the vector u with direction vector a, if you project u onto a, you're going to get this vector W1. That's what the projection theorem tells you. So, and I'm really hoping that was on the screen when I pointed to that, because I got a bit overzealous and I wasn't even looking at my screen. But in any event, so that's going to give us this W1. Now, guess what the terminal point of W1 is going to be? It's going to be exactly that point that we identified at the beginning that we didn't have access to, that we couldn't find. So that's really good, because we essentially have that point. We could draw the vector W1 so that its initial point is Q, which we already have because we picked that ourselves at step 1. Now whatever the terminal point of this vector is, that's going to be that point on the line that's closest to P. So we could calculate the distance between those 2 points directly, and that would solve the problem. However, it's even easier than that actually, because if we found W1 to be this vector, we can find this vector right here by just, well, that's our W2, right? That's our W2 in the projection theorem. That's this vector right here. So let's just add that onto step 4. So and W2 is just going to be U minus W1. So this is W1 right here. Pardon me, W2 I meant to say. So this is W2 right there, and you're going to form a right angle, which is exactly what we want. And guess what? Take the norm of W2, and that's going to give you the distance between this point and this point, which is exactly what you want, and that's going to answer the question. So the distance that we want is given by the norm of W2, and that is an application of projections. Now this has all been fairly abstract, and we're going to do an example on the next page, but for now I just wanted to give you an overview of what you would ever care about projections for. This solves the problem wonderfully, but I would challenge you to spend a few moments thinking about the fact that do you really need projections to do this? And the answer is yes. If you didn't have the projection available, if you could not get your hands on this W1, then this point Q is useless, right? Because it was just a random point that we picked on the line. So this W1 is crucial because it essentially turns this random point into exactly the point that you wanted. Now, what if we picked a different point Q? well, if we follow the steps carefully, then our W1 would change to compensate. But if our Q was back over here, then W1 would have ended up just being a longer vector. And it still would have taken us right to where we wanted to go. So that's one example of why projections can be really useful.